Okay, so for another method to get the time complexity of a recursive function, we have the recursion tree method. So previously we used the recurrence relation and then expanded it to a point where we can find a certain pattern. Here we use the recurrence relation to generate a recursion tree, or it basically it's a simulation of the function calls inside the function calls necessary to accomplish the function. So this won't be much. You won't appreciate this with the factorial function, which doesn't really make a tree. So let's use a different function here called Fibonacci, which gets the nth Fibonacci number. So I think you should be familiar with this. The Fibonacci of n is equal to the sum of Fibonacci of n minus 1 and the Fibonacci of n minus 2. And then we define the Fibonacci of 1 to be 1, and the first Fibonacci number to be 1, and the zeroth Fibonacci number to be 0. So the recursion tree would look something like this. So the Fibonacci of n calls Fibonacci of n minus 1 and Fibonacci of n minus 2. The Fibonacci of n minus 1 calls Fibonacci n minus 2 and Fibonacci n minus 3. And then the Fibonacci of n minus 2 over here calls Fibonacci n minus 3 and Fibonacci n minus 4 over here. And then it just splits and splits until we reach Fibonacci of 1 or Fibonacci of 0. So for the recursion tree method, what we do here is we get the sum of the runtimes per level and then add the runtimes of all the levels together to get the total running time. So the Fibonacci function itself, without the recursive call, is just runs at constant time since it's just doing an addition. So for level 0, we can say that we have a C, a runtime of C. For level 1, we have a runtime of 2C, where C is the constant runtime of a single Fibonacci call. And then for level 2, we have 4C. For level 3, we have 8C. And then as we go on and on, you see that the number of calls per level is double that of the previous call. So that just means we have the sum of the powers of 2 over here. And then our last level, which is not exactly 2 to the n minus 1 since only 2 calls would exist there, but we can almost estimate it to be equal to that. So uh, since the total runtime will be the sum of these, and since we just estimated the latter part of it, we just make this a less than sign, which is okay since we're just getting the worst case, the asymptotic big O notation of the time complexity. So remember that we're only interested in the fastest growing term in the expression here, and the fastest growing one would be 2 to the n minus 1. Now, the exact runtime might be a little bit less, so maybe somewhere in the middle uh, where the number of terms in the tree is maximum, or the number of terms in the level is maximum. But we can pretty much see that it's just n minus a sum constant. And then no matter what constant we actually subtract to n, we always get that the big O will be 2 to the n. So so that's the recursion tree method. So it's more graphical and a little bit more wordy. And words as in wordy as in uses a lot of words. So It's an alternative method whenever you can see you don't get to see the pattern when you use the substitution method. So yeah, so that's the recursion tree method.